GCSE Physics Boosters, moments. This video is about moments. In a moment, I'll tell you what they are. Now, look at these diagrams. What kind of force do you need in each case? What kind of force do you need to turn a tap on or off, to tighten a bolt, a nut, to turn a screw? What kind of force do you need to make wheels turn, to open a jar, to make one of these spinner things whiz round? Now, to make something turn, we need a turning force, and in physics we call it a moment. You can also call it a torque, T-O-R-Q-U-E, but we're going to call it a moment. To make something turn, you need a turning force, you need a moment. Now, this diagram shows how you can produce a moment, how a force can produce a moment. We say that the moment is about a pivot. In other words, the turning force is around a point called the pivot, which in this case is the middle of the nut, is the pivot. And the force F is producing, in this case, a clockwise turning force. So when you push down with a force F, that's going to turn the nut clockwise. So if you want to tighten the nut, this is what you would do. What does the size of the turning force depend on? Look at the diagram. How do you think we could make the turning force bigger? Look at this equation. This is how we work out the size of the turning force. The moment, M, is force times perpendicular distance. It's the distance at right angles between the force and the pivot. Moments, capital M, moments are measured in Newton meters. Forces in newtons, distances in meters, moments are in Newton meters. By the way, they're not in joules, because for joules, work, force times distance, the force and the distance have to be in the same direction. Here they're at right angles to each other. So it's not a joule, it's just a Newton meter. So moment equals force times distance. In this example, if the distance is 15 centimeters and the force is 20 newtons, calculate the size of the moment. And I'll show you the answer right now. It is, so M equals force times distance equals 20 times 0.15. Yeah, look, the distance has to be in meters. And that will give you a clockwise moment of 3 Newton meters. That's our turning force, 3 Newton meters. Here are some more examples for you to have a go at. So have a go yourself, pen, paper, calculator, and I'll show you the answer in 3, 2, 1. And there you go. So top left, it's the same question really, different numbers. Moment is force times distance. 30 times 0.2 is 6 Newton meters clockwise. Top right, the guy on the diving board. So his weight will be 750 newtons if little g is 10. And so it'll be a clockwise moment about the pivot, t'other end of the diving board, 1,500 Newton meters clockwise. The wheelbarrow, the guy applying this 40 newtons force, so this will be an anti-clockwise moment. The pivot will be the middle of the wheel. That is the turning point, the pivot. So 48 Newton meters anti-clockwise. Now, the seesaw, there are 2 moments. The girl on the right, well, she's going to produce a clockwise moment. The girl on the left will produce an anti-clockwise moment. And so there's 2 moments there, clockwise and anti-clockwise. You'll notice that one of them is bigger than the other one. And because of that, our seesaw isn't going to be balanced. So let's talk about this. The clockwise moment is bigger than the anti-clockwise moment. This system is not balanced. Okay, For a system to be balanced, then about the pivot, the moments have to be the same. Have a go at this. Can you figure it out? Will this system be balanced? Work it out. Work out the clockwise moment. Work out the anti-clockwise moment. Will it be balanced? And what you should have written down on paper is something like 3, 2, 1. So our clockwise moment is going to be 20 times 1.5, which is 30 Newton meters. Our anti-clockwise moment will also be 30 Newton meters. The two moments are equal and opposite. If you like, there is no resultant moment. Do you remember resultant forces? So it will be balanced because the two moments are balancing each other. Here's a very exam-y type question, this one. This crane has a movable counterweight, which has a mass of 1,200 kilograms. Explain why the counterweight is needed. If the crane is lifting a load of 3,000 newtons and this force is 8 meters from the pivot, how far from the pivot should the counterweight be? So have a go at it, and I will show you the answer in 3, 2, 1. Okay, so now the load would produce an anti-clockwise moment. Here's our load there, and the anti-clockwise moment. So we've got 3,000 newtons, and I said that this distance is 8 meters from the pivot, and the pivot is this point here. That's the pivot. So we're going to get an anti-clockwise moment of 3,000 times 8, which is 24,000 Newton meters. So basically, we're going to need a clockwise moment to balance it. This is an anti-clockwise moment. We're going to need a clockwise moment, and that is why the counterweight is there. Now, if the weight of the counterweight is, if its mass is 1,200, then its weight is going to be 12,000 newtons. 12,000. So 12,000 times that distance has to equal 24,000. So that distance needs to be 2 meters. A load would produce an anti-clockwise moment about the middle of the crane. A clockwise moment of the same size is needed to balance this. Otherwise, the crane might fall over, which wouldn't be very good in a city centre. Okay, so there's the math, 2 meters. Levers. We need to know a little bit about levers. Levers can be used to transmit forces using moments. So there's a lever. The force in is called the effort from our muscles, and there's an output force, and in this case the output force is bigger. We're using this lever as a force multiplier. Levers can be used to change the direction of a force or to make a force bigger. There are some examples where they actually make the force smaller but the distance bigger. But anyway, levers can be used to transmit forces using moments. Here are some examples of levers. A nutcracker is being used as a force multiplier. In the wheelbarrow, yes, we're lifting a heavy load. It's a force multiplier. And the claw hammer. And lastly, the brake lever on a bicycle is a lever. And that's being used as a force multiplier as well. And lastly, we need to know a little bit about gears. Gears can also be used to transmit rotational forces. Okay, they can change where the turning force is acting. If you want to get your turning force from the engine to the axle of the car to make the wheels go round, then you would use gears to do that. And they can make the turning force bigger if needed or smaller. So levers and gears you need to know a little bit about.